back, you guys. A quick warning to those of you who I suspect are watching on YouTube right now. Unfortunately, this used to happen to me at Stanford because I taught in their professional development program, which had like real cameras, and there were days when I taught to an empty room. The class still got really high ratings, so apparently it's just people that weren't coming. So again, remember like we said on day one, if attendance in lecture drops enough, I'm gonna do something crazy like have the videos play backward on YouTube or something. I mean, like really, you're supposed to come to class. It's for a backup, okay? Before we get started, are there any questions? You know that your next assignment is due a week from yesterday. So I know some of you guys have gotten started, which is great. If you haven't, you should, because I've gotten grumpy emails from some people that appear to think that there's some problems there. So I think we've clarified them all, but it does indicate to me that you should get started. Are there any questions about the assignment? Oh, and your grades. Everybody's favorite topic. The TAs have been diligently grading your grades, but it appears that you actually weren't able to see them for some reason. So we contacted the MIT people and gave them a hard time. And there's like some mysterious checkbox on my webpage that I was supposed to check that I didn't know. But anyway, so if you log into Stellar now, you should see grades for, let's see, assignment 0, assignment 1, NanoQuiz 1, and NanoQuiz 2. If you see grades for more than that, you should let me know because they haven't been graded yet. Okay? Are there any procedural questions before we get started? Your next assignment is a fun one, by the way. Doing all the skinning stuff is pretty cool. Yeah, start it now, again. Okay, folks, so let's get started with our technical content again. So today, as promised in our last lecture, we're going to be talking about physics, right? So remember sort of the way that AP7 is organized, right? We start from how do you generate content that you're going to display, right? We talked about splines and shapes. Then we talked about animation, how to get, how to express motion. We're slowly building up to how to actually draw it. But in terms of animation, last time we talked about things like procedural animation and so on, right? Hierarchical modeling. Today's topic is physics, right? In particular, if you watch certainly kind of live video style movies, but even cartoons, right? All of these things are operating in some kind of physical world, whether it's applying F equals ma or its own physical laws. And our job today is to talk about how to engineer computer systems that can actually fill in that style of animated content without having the artist specify a bunch of frames, right, or keyframes, right? Like for instance, if I have a big pile of balls and I drop them on the ground, I probably wouldn't want to animate the path of every single ball as a function of time. It seems like kind of overload, seeing that physics are dependent on time. So that's our job for today. In particular, we're going to talk about a technique called particle systems, which is what I would call physically based animation. Remember, we introduced this term in our last lecture, and it's essentially a cop-out, right? It means that we're not doing actual physics in this class. You should take course 18, course 9, course 8. I don't care. you should go to the physics department if you want physics. We're here to do computer graphics, which is physics-ish, but obviously, if you're watching Transformers, you know that it's not real physics, right? In fact, there's a great example of that when I was working at Pixar. There was, my boss at the time was working on this like WALL-E robot. WALL-E was the robot that was cleaning trash on Earth. And they made an actual robot, like an actual WALL-E robot that they were going to use, on like news segments as like kind of a cute promotion thing for the movie. And in doing so, they thought, oh, what we'll do is we'll take the computer animators and we'll just have them control this WALL-E robot. And this was a disaster. And the reason was that, like if you look at the typical motions that WALL-E was making in this film, right, they're kind of bombastic because it's animated. Like a single arm motion for WALL-E was enough to like launch him off of the face of the earth. And so, there's two reasons why we don't necessarily want to do actual physics in computer graphics. One is that sometimes it's not what the artist wants, and the other is that it's computationally expensive. When in reality, all we want is something that looks like acceleration. Right? And it turns out that what your eye perceives as physics is neither accurate nor sometimes is it physical, right? Which is one of the really interesting things about perception. So anyway, if you'll recall from our last lecture, we called out a lot of different types of animation, right? There's keyframing, where essentially the artist explicitly puts a few poses in time, and the computer system's job is to fill in all the stuff in between. By the way, you guys remember, what is it called? The people that fill in the space between the keyframes? In between. Yeah, it's not a hard word to remember. Yeah, there's a procedural animation where, like, rather than just giving an animation curve for every single object that I'm moving around, procedural animation is like I write a piece of code that generates the animation curves, right? So remember the example was a clock, right? So you could animate a clock by ticking forward in time and figuring out where all the pieces of the clock went, right? So your piece of code there would be the procedural animation system. And then today we'll talk, and next lecture we'll talk about physically based animation, where those types of objects are interacting with things that open the real world. This is usual for effectively smoke, water, fire, sparks. And for the most part, we're going to do pretty heuristic things. Like we're going to look at smoke and say, it seems like smoke follows paths that look like this. So we're going to make graphic systems that make paths that look like this. Yeah? You could get philosophical and say, well, that's roughly what Newton was doing as well. But I won't try to make that claim and rather just say that we're not here to capture like a measurement. We're here to make things that look like. They're two different things. Okay. Of course, in physically based animation, what we will cover in this class is particle systems, and then in our next lecture, we'll talk about how to simulate cloth, which is a topic that's very close to my heart. I actually implemented a cloth system for an animation studio. But something that we're not going to talk about here is continuum mechanics and fluids, right? So if you're looking to make the next, what is it, Pacific Rim, and you have, transformers and what is it, Bumblebee and Octopus 9 or whatever its name is, and they're all going, they're sloshing through the fluid and there's things dumping every which way. That's unfortunately actually requires some pretty heavy duty physics that's outside of the scope of this class. However, it does use a technique called finite element method, which is covered in my advanced class A3. But that may not be offered this year. It depends whether they need an instructor for convex optimization. But we'll come back to that. So for today, we'll talk about registry. So in physically based animation, we're solving the equations of motion, which is probably a phrase you've already heard in physics class, which apparently is course 8. And and so when we say equations of motion, essentially this is like F equals ma, right? It's the thing that's determining how stuff moves as a function of time. And when we say solving equations of motion, that's really exactly what it is, right? F equals ma doesn't explicitly give me the path of a particle, but it gives me a relationship between the forces and its acceleration, and then from that you can deduce the path. And so that's our job here today. But unlike physics class, where maybe you're trying to compute closed form expressions for like very simple things like ball bouncing, in physical simulation in video games, we want to do it using a numerical technique, right? We just want to step it forward in time so that we can have very complex relationships between the objects that are seen. Okay, so in the physically based animation world, of course, there are lots of different types of dynamics, and it really follows some sort of hierarchy. Right, so at the very base, right, and it more or less follows what you probably saw in 8.1. Would that be mechanics? I don't care. I don't care. I keep trying, and it's just all good. So, right, so if I have a particle, so this would be like a point that's moving around, and the point has mass, but it doesn't really have orientation, right? So there's no notion of angular momentum. So I think when you learned about, like, the basic physics of gravity and equilibrium and so on, you probably were doing point dynamics. Right? Then from there, the next step up would be rigid body dynamics. And the difference between point dynamics and rigid body is that rigid bodies can rotate. Right? If I rotate a point, what do I have? A point. Like it didn't change. Right? Whereas if I rotate a cube, I have a rotating cube. Yeah? And in fact, as we know from our last few lectures, if I rotate a cube in one axis and then another, or if I do it in the reverse order, I'll get a different thing. Right? So it's a pretty complicated dynamical system. And then, of course, beyond rigid body, probably what's the most popular area in the computer graphics literature to study as a research problem are things like deformable bodies. So here we take this famous 3D bunny model, which I think you loaded in your first assignment. Did they load the bunny or the teapot? Nah, too bad. Next time we'll have to do the bunny. And one of the things you should do is hop on Google and just search for like ways that people have abused this bunny model. It's like kind of the basic test case for a lot of physics simulators. So here, the bunny starts out as a piece of wax, and apparently they melt the left-hand side. Yeah. So I think there's a whole website where people have collected like weird stuff that simulation people have done to the bunny. Okay. But for today, we're mostly going to talk about point dynamics, and the idea is that we're just going to think about physical objects as little concentrated points of mass that don't even have an orientation. It's the simplest possible case, and then we'll expand outward from there. Right? So in the next lecture, when we talk about cloth, obviously orientation will matter quite a bit. And so these are what we call particle systems. And certainly in the history of video games, this is probably the earliest appearance of physics. Right? The particle systems, where it's literally just like little dots moving around, maybe they're interacting, maybe they're not, can get remarkably sophisticated and interesting behavior, even with just following very simple rules. So for instance, in this image here, the particles are all following independent paths. Like these are just a bunch of parabolas. But when you place them in a nice way and give them a nice initial velocity, it kind of looks like a fluid. You can see the kind of argument I'm going to be making a lot of in our physics lecture. Like, yeah, it's kind of looks like a fluid, so it's good. And the thing is that calculating this, you don't even have to solve that because it's just parabola. So you can get remarkably nice behavior with remarkably simple dynamics. Okay. So in the particle systems world, which you're going to implement in your next assignment, by the way, the basic vocabulary words are on the slide here. You have emitters, which generate particles. That would be like the bottom of that little fountain, right? Those are points that are, peeing things out. There's external forces, either from a force field like gravity, or you can have forces that are from interactions between the particles, right? Like maybe you're simulating planets, and the pull of the planets toward each other is what's creating the interesting motion. And then your job is to integrate the laws of dynamics from motion. Right? And it really is an integral, right? Like remember, like F equals ma, a is a derivative, and if you want the path, then you got to undo the derivative, and that's an integral. Yeah? That's fundamentally what we're going to do, although when we use the word integral, it's not going to be like some obscure calculation that you substitute the right thing and get some number like you did in calculus class. We're just going to do it in a number crunching way. And that's the sort of the standard. And of course, one of the things we know about the real world is that it's essentially random, right? That we won't have a fate versus free will discussion in this class, but from at least a macro perspective, when you look at the physical behavior around you in the world, there's particles moving every which way, right? And there are two ways that you could try to capture that, right? You could either capture every possible interaction between every little tiny object in the world, or you could just perturb them a little bit, and you get roughly the same thing, right? In fact, a lot of areas of continuum mechanics really formalize that in physics. It's not even that incorrect to say something like this. And so randomness plus these basic, very kind of low frequency physical simulations will get really, really nice effects in practice. And this includes things like sand, dust, smoke, flames, water, you mentioned. So all kinds of stuff. So for instance here, again, remember you saw that particle system before. Essentially, all we did here was take exactly those particles and give them kind of a shiny texture, and you can see that it looks awfully like, a lot like a sprinkler, right? And so particle systems are not just like a toy. Example, like the next time you open your favorite video game and you look at kind of the secondary motion, like the uninteresting stuff in the background, I bet a lot of it will have to do with essentially moving particles around and then just having like a little billboard that's being rendered as a particle system. Yeah. Okay, so there's a sprinkler, here's some fire, which I believe is also essentially from a similar particle system. Where essentially all they're doing is they're having particles that want to move up-ish and want to curl around a little bit. Right? These are things you could kind of come up with heuristics for. And then they just texture them using yellow. Right? So it's remarkably nice behavior for very simple stuff. Cool? All right. Yes?
Are particles points, or are they like small bodies?
It depends. So for our purposes today, they'll be points. Later in future lectures, we'll talk about mutation and interaction. All right. And so a great example of a very complicated particle system would be crowd simulation. Right? So let's say that I want, I spend a lot of time in Costco, and maybe I don't get that experience when I'm home alone, and I'd like to experience it in a video game. Then I can give all of my virtual characters little shopping carts and treat them like little particles that are moving around, and give them very simple rules, right? Like if you get too close to each other, go the opposite direction, because as we all know, you don't want to have a social interaction in the grocery store. And roughly, when you're simulating very large environments with lots of characters, even those simple rules are enough to come with some kind of interesting stuff. That's again, sort of secondary motion to maybe the primary stuff, which is what you really want to focus your animation effort on in your video game, right? So maybe you keyframe the really key features that are like the things that you're going to interact with, right? You can hire artists for that, and you have some cheap engineer like me that can fill in the background stuff to just look interesting. Yes?
Some of these rules have different priorities, because it looks like there's people intersecting the one, right?
Yeah, so I'm guessing this is not a high quality simulation. So you're absolutely right. It looks like these two ladies are not only the same person, they're also walking through each other. So apparently whoever implemented this did not do a great job. But there are better systems out there for avoiding. Yeah, absolutely. In fact, there's some really interesting papers at SIGGRAPH that essentially involve like how do you understand humans as dynamical systems, right? Like so, you guys probably have read like it's one of these great topics on Wikipedia. If you're bored, you just start reading. This is like giant. You know, I think if you read about these disasters that happen where there's so many people at like a football game that suddenly, and there's like an emergency inside of the stadium and they all have to escape, then suddenly people begin acting like particles in a particle system instead of like rational beings. It's absolutely true. This is like a well-documented phenomenon. And roughly the same people that do that kind of science and engineering of like how do I optimize the shape of my football stadium so that when people turn into idiots and they want to leave, like they do it in a systematic way. Those same people are the ones that are engineering some of the secondary motion in this video. Right? So for instance, there's this interesting paper last year that involved like when people walk past each other and there's a narrow space, how do they do it? Right? And there are a lot of different options, and probably if you took this terrible system here, they'd walk through each other. But you know, like for instance, Tao and I both have mathematical backgrounds, so if we walk past each other, we take a large space, right? And so anyway, capturing and documenting this stuff is a great intersection between philosophy, or not philosophy, like psychology and computer graphics. That's a very well studied and interesting design. Okay, we don't want to do this. And so we're going to talk about particle systems today, and the next time we're going to talk about a very famous technique for cloth simulation, which essentially is a particle system, where you're going to think of your cloth as this big network of little points linked together into triangles. That should sound familiar from your zero. And essentially the rules that are governing the dynamics are going to come from the edges of that triangulated mesh. So, right, of course that'll be the beginning of this story. You know, people in computer graphics work very hard on cloth simulation. Here's an example of what that looks like. This is a test case from Ron Fenku's group at Stanford. And there are a lot of things to notice here. Obviously, this is not a collection of particles, for one thing. For another, they have folds, and probably the most challenging thing to deal with in a test case like this, which you might not even realize, is that the folds can't interpenetrate, right? And so if you have this surface, which is composed of like, what, maybe a million triangles, then you have to check every single pair of triangles, see if they run into each other, and then resolve that collision as you simulate forward in time. This is a really challenging problem, and one that people still study today, including whoever's making upstairs. Is there a microphone that's on?
There's some event of the room below us.
Well, I know there is a microphone in this classroom. Yeah, it's coming from yeah, they're all on mute. Yeah. Hey! I'm just going to mute everything. If you're the person with the microphone, I apologize. Right. So particle systems actually are used in modern physical simulation. A great example of that, and one that seems to be very popular final project idea in 837, although I'm not sure I'd actually recommend it because it's difficult, is something called smooth particle hydrodynamics, or SPH. These are fluids that are composed of little particles. And the trick is you don't draw the particles, you kind of construct a surface out of them, like, you know, take the union of the little balls around them, and you get a pretty interesting fluid motion. This is called SPH, and you probably have seen SPH fluids in movies. If you look really, the way to tell this, by the way, if you watch a film of fluid splashing that's virtual, and you look at the little droplets that come off, if they're all perfectly spherical, then it's probably an SPH fluid, right? Because that's what they're doing. They're constructing fluids out of little spheres. So you have these little droplets that come off and don't merge together. You can see the kind of the basic building block, right? Especially if all the droplets have the same size, okay? That's the dead giveaway. But of course, more modern systems do all kinds of cool stuff. So this is already a few years old. It was 2008. And you can see here that there's a combination between, I think this is grid-based fluid, so I got a grid and I just keep track of which cells have fluid and which don't, with spray, which is a set of particles. Yes?
How long would something like this take to render?
Oh gosh, let's see. I was around Ron's group when they were working on this paper, and I think it was in the order of hours per frame. Yeah, this is very expensive. Yeah, when the particle systems we do in this class, obviously we will not have you do that because we wouldn't have enough time to finish your assignment. But there were some students in this class, for example, that did very high resolution. Like actually the winner of last year's 837 contest, which I think Linda linked the videos from his thing on the Piazza page, like did a really high fidelity smoke simulation, and I'm pretty sure he needed a lot of time per frame. No, that was no time. At least if it was very impressive. Yeah. the second place good, the caustics, like light bouncing and interacting with glass, which is also expensive to run. But we'll do that in a few minutes. Okay. Of course, in video games, we don't have the luxury of a couple hours per frame. We have to do 29.97 frames per second. And so, you know, if you want this guy to drool a little bit, I guess, like he's getting punched, then maybe you just emit a particle rather than doing like a very complicated, you know, fluid. Right? And even so, you need some pretty cool behavior. So let's see if we can play this. By the way, I will for you. And you can see the particles. Right. So you guys yeah. So modern video games really do use this stuff and just couple it. And the idea is that where I want really, really good physics, that's where I want to put my CPU time. For like the little schmutz that's coming off of the guys is being punched, that doesn't matter so much. Yeah? Okay. Right, so in other words, it really ranges from like totally boring heuristics that kind of look good to real physical simulation. Like state of the art in like actual numerical partial differential equations, a lot of it comes from the computer graphics world. Right, so for instance, I happen to be the professor in charge of the Center for Computing, like Computer Engineering seminar series at MIT. So like all the mathematicians that come and talk about simulating like turbines and like heavy duty stuff. And one of the speakers that we have coming this time is from an animation studio. It really is doing state of the art stuff for simulation. Okay, but for our purposes, really, it just boils down to integrating ODE, and that's what we're going to talk about today. This is true for any simulation, for air, for water, for particles, for whatever. It's all the basic, the same machinery. So here there's like very voluptuous hair on, I believe, a 3D scan on like a grad student or something like that. In each one of these cases, these are very challenging cases. Okay. So we're going to talk about particle systems. This big collection of particle-like masses, and every particle is going to be described with just a big vector of information. Right? So in particular, I got to keep track of where it is. I got to keep track of its velocity, and then there's other information that might be useful for rendering. Things like its age, its color, anything that you need to make that believable behavior that you cover. And then the motion of your particle is going to be influenced by external stuff, right? Like a force field that's kind of sitting underneath the particles that moves through, as well as their interactions. Although, of course, the latter makes your system much more expensive computationally. Right? Like everything's moving independently, then it's just like this giant parallelizable thing. And otherwise, you have to collect all those influences and integrate them forward. Yeah. So we create those using generators or emitters, and maybe we do it kind of random way, right? So for instance, in that sprinkler example, maybe the orientation of your individual particle is perturbed just a little bit, so I get that nice, whatever you call it, shape of particles. By the way, typically you give a lifetime to your particle, so you don't want it to like drop through the floor and just keep going down for the rest of the video. Right? So eventually maybe just remove it for and typically they're actually dependent, which I think comes as a surprise, right? Like that sprinkler example is a great one, where those particles were not interacting. Right? They were just following parabolas, but we still got a really nice motion. You know? And that's, I think, a really cool and surprising thing, that just a tiny bit of randomness, perceptually to humans, looks like physics. And video games really leverage that in their physically-based animation systems. Right, so let's talk about how to do that sprinkler. So maybe I have a long linked list, or even an array I think is probably fine of particles. The reason why you might want to have a linked list is just that, if I'm emitting 1 particle per second and I only remove it when it passes through the ground, for example, then it's very hard to put a bound on the number of particles that I have. So maybe rather than doing that, I just keep track of some kind of data structure that can just keep adding to my list of particles. Yeah. So I initialize it to be empty. I have some initial information about how random the colors and the spread of the spray is that maybe the artist has designed. And then for each time step, my emitter generates some new particles. Right? So roughly, it'll make some kind of pointer-like object. It'll give some information. So here the velocity is up plus some random number, right? Because I want to perturb it just a little bit. And then I add it to my list of particles in the world. Yeah. But it's a pseudocode, more or less, for what you'll implement in your assignment. I think you could have guessed what this looks like, right? This isn't too complicated. And then, well, now time is moving forward, so I don't want my particles to just be emitted and stand there. Right? They have to follow a path. Yeah? And so that's our next step. So now, well, if I have velocity and I have position, a reasonable way to update your position would be to take velocity multiplied by dt, and now you have a change of position. Yeah? And that's more or less a fancy, well, an unfancy way of describing ODE integration. Yeah? And then, of course, you can do the same thing, right? The d velocity dt has another name. What is it? What is it, everybody? That's the derivative of velocity with respect to time. Yes, good. Acceleration. So if I want to step forward velocity, one thing I could do would be add a little bit of the acceleration, which for particles that are just moving in gravity is a constant. It's an easy word. Yeah. Then finally I draw. So does the basic particle system make sense? Really, really simple stuff. Cool. All right, and indeed you can even play with it. So let's see if we can get this simulation to run here. Aha! Yeah, so here's a particle system. And this is running in the browser, so you can, anyway, it's linked in the slide. You can play with it. Somebody has code here. You can mess with the code and get different particles. And notice that these are all independent, but it still looks pretty nice, right? And so all this is doing is having particles move along parabolas, and the older they are, the darker their color. That's it. Okay. Cool. All right, so now we're going to do math. Enough of these pictures. And of course, my timer is on, so we can't tell if I'm over. Okay. And in particular, we're going to talk about ordinary differential equations. How many of us know what an ODE is? Ordinary differential. What's that?
I used to.
Used to. Good. That's yeah. So we're going to talk about a little bit today, right? So remember that F equals ma is a relationship between the physical system that you're trying to solve and derivatives in time, right? And then your job is to get rid of those derivatives in time, right? To just get a path. And that, in general, is an ordinary differential equation. Right? Now, of course, F equals ma, how many derivatives are there? There's two, right? There's a second derivative. And what I've written for you is a derivative, it's just one derivative. Yeah? So it looks like I've done something wrong, right? I want to do physics. Why is this it? So we'll come back to that momentarily. But for now, of course, an ordinary differential equation, it looks like that. Right? So dx dt, where x is a big vector of all the information about your system, like the positions of all the particles, is some function of your current configuration and time. Yeah? And so, for instance, if I have springs, right, then this F would be the spring force between all the particles, and this dx dt here would seem a little fishy. Yeah? Okay, we'll come back to that. So this is called an initial value problem, right? So I'm given the configuration at time 0, and I want to evolve it moving forward in time. Does anybody remember what the opposite of an initial value problem is called? Bueller?
Boundary value.
Boundary value problem. Thank you. So a boundary value problem will be like, I have a system at 2 points in time, and I'm trying to explain how one got into the other. Right? So the boundary, there's 2 points in time, as opposed to the initial value, which is 1 point in time. And I'm going to talk to our master problem about teaching that. Okay. There's Newton. I wish I had that kind of hair. And of course, he tells us that physical systems are organized not by first derivatives, but by second derivatives, right? The F equals ma is the basic relationship here. And really, notice hiding inside of that is d squared x dt squared, which is the thing that we want to get rid of, right? We want x of t. We don't want dx dt. Yeah? But of course, what I gave you in the previous slide was a first order equation, and this is what we call second order, right? There's two derivatives. Yeah? But what I claim is that actually first order is enough. Yeah? And how can I do that? So remember that I have in such a system, it's like x prime of t equals, right? This is like a kind of an abstract way of writing f equals ma. Yeah? Okay, so let's add a new variable. In fact, let's call it v. Yeah? So what does v stand for? V stands for velocity. Yeah? So in particular, v prime of t is, well, right? So I didn't really do anything to it. And we know that velocity, so x prime is equal to v of t, right? Now look at the left-hand side of this thing. These are all first derivatives, yeah? So what can I do? I can exchange a low-dimensional problem with many derivatives for a high-dimensional problem with fewer derivatives. You see that? In other words, I doubled the dimensionality of my problem. I now have a variable x and a new variable v. And the relationship between x and v is this second thing, right? X prime equals v. Yeah? But when I did that, notice that now I only have to worry about v prime of t, like like that. Yeah? So I could write this in a slightly fancy way and say, so what is x prime? It's v. What is v prime? It's f of x. Yeah? This is a first order ODE whose solution obviously gives you the second order behavior. Everybody understand this reduction here? Okay. So this is, so in other words, a different way of putting it is if I give you a piece of software that can only solve things with one derivative in it, you're good. Okay. Does that mean that if I give you the best piece of software in the world for solving a first order ODE, then I should use it and expect the best possible software in the world for a second order one? No. This shows that you can solve second order ODE using this reduction to first order, but it doesn't mean you have to, right? So you could come up with specialized software that just deals with second order stuff. A great example of that is a leapfrog algorithm, or something, what is it, Stürmer Verlet, I'm not German, so I can't say his name, which only applies to second derivatives. But any first order thing does apply in the second order case. I know that was like a lot of like circular words, so hopefully that works. Okay, great. So here's Newtonian mechanics, and again, here's our reduction to a first order ODE. And the idea is just that you double the number of unknowns, right? You add as your unknown v of t. Yeah? And obviously, the relationship between x and v is ds dt. Cool. Okay. So in other words, when we solve our class system, we're going to use a first order ODE. Right? We're not going to do anything too fancy now. Okay. And why reduce that? Well, essentially, like you can imagine, for example, maybe your video game actually also has a third order term, like your jerk or your car matters. You don't want to have to come up with a specialized piece of software every time you change your ODE rule, right? So sort of what we're after is the simplest possible thing that will solve as many equations as we can write down. Right. And as I mentioned before, there are methods that are specifically for second order problems that are more accurate or more efficient than the ones we'll talk about. Okay. By the way, if this notation is still a little confusing to you, that I've coupled, like this still kind of looks like there's two variables here, of course you can cheat even more as a mathematician and define capital X to be the couple little x and little v. And now look at that. Now I have d capital X dt equals f of capital xt, where f is defined to be in this complement. Does that make sense? So really, you know, from math's perspective, it doesn't care that the first maybe 3 are v and the second 3 are x or whatever. This is just one giant 6 division. Okay. Right. So in a particle system, in fact, this trick is going to be really important, because what do you think I'm going to do? Well, now I'm going to take all of the particles in my system and I can stick them all in one giant vector with their velocities. And now I have a first order ODE and all of these things that captures not just the derivative of velocities acceleration, but also that the particles didn't interact, right? These capital F's could, for example, include conditions of pairs of particles if they're connected by spring. Cool? Okay. So, right. So in particular, when the particles don't interact, then obviously each one of these guys only depends on that piece, but when they do, then maybe this capital F actually depends on the whole vector, right? Like the particles near me affect the forces that I feel. So this is all like essentially just mathematical formalization of what we probably already know and have solved in physics class. Okay. So one other little vocabulary word that's useful to know, there's something called phase space. By the way, do you guys remember this from physics class at all? Phase space? That's okay. Phase space is exactly what I just showed you. So the idea is that, like for instance, let's say I'm solving a one-dimensional problem, like I'm simulating a particle on a spring that's just kind of doing its thing on a line. Then really I have a two-dimensional problem, right? Because I've added two variables, x and x prime. So if I look at the curve that I draw in x prime space, that curve would be a curve in phase space. So phase space is just this higher dimensional space that plots both position and velocity. That's all it is. Right? So for instance here, can anybody eyeball the thing on the left and tell me what phase space this is? So x is velocity, or is position, and y is velocity. Yes? What was that? Pendulum. Yeah? Right. And how do you see that? Well, essentially, if I give something a good tip, right, then I zip around in circles, and that's what you're seeing down here. Right? Your velocity keeps spinning around. And around the center, you just go back and forth. And so anyway, you can see relationship, but what you can't see in this plot is time. Right? You just see sort of where positions go next. Okay. So if we integrate ODEs, right, we're solving physical systems. This is what we call numerical integration, or if you want to be fancy or at a dinner party, you can call it quadrature. And quadrature is all about how to integrate stuff as a function of t or just about anything else. Incidentally, quadrature is like a really, really classical, old school problem in numerical analysis. We're all going to scrape what you need for like basic video games rather than really advanced active things. Yeah. So we'll talk about the simplest one today, and then on Tuesday we're going to give you all kinds of cool quadrature techniques, because what we're going to realize is that the one that I'll tell you today is quite inaccurate. Right? In other words, if you take like big time steps, like that dt is a big number, you'll get a pretty bad approximation of your physical system. All these things converge as t gets small. Okay. So in general, if I gave you this ODE, dx dt equals fx, I think you guys would all, even like if you just got out of high school calculus class, you would all give me a reasonable algorithm for solving this thing, right? Because roughly, if I multiply both sides by dt, we know we can't really do that, but whatever, then what do I get? I get dx equals dt times f. Yeah? So what could I do? If I have x at t, how would I get x at t plus dt? Well, roughly, I just add this thing to it. Yeah? And that has a name. That's called forward Euler integration. And so in the forward, really the forward Euler algorithm is roughly what's going on in these processes. It's really not that complicated. So it computes this vector of positions and velocities. It computes the forces, which is essentially some x prime. And then it adds just a little itty bitty bit of that to your current estimate, and it iterates. Yeah. Right. So that's the basic trick. This is called Euler's method. I usually, in my textbook, it's forward Euler. In graphics textbooks, it appears to be Euler's method. And essentially, what do? You say, okay, well, I'd like to go to a new time, which is t naught plus h. So what do? I just add h times f. Does everybody understand this algorithm? I think it's very intuitive. And so one way to understand what Euler's method is doing is following a piecewise linear path. Do you guys see why that is? I mean, essentially, let's say that I'm in phase space, and I have some position, right? So then when I evaluate the function f, that draws like a little arrow, right? That's telling me where I want to move. And then what do? I scale that arrow by dt, and then this is my new position, and I get some new arrow, which is my new velocity. Yeah, I scale that by dt, get a new position, and so on. Yeah? So look at my path, right? It's like this line segment and that line segment. Just move along little straight pieces of straight lines. That's why we say that it's a piecewise linear path, right? Every piece is linear. Cool? When we talk about, oh, I forget the name of these integrators. There's RG3 is not it. It's RK4 integrators are going to essentially replace these paths with like polynomials, just like what we do in small class. The great thing in this class is nothing, you can't forget anything, because it just keeps coming back. Okay. So visually, I think we could all draw a reasonable picture of what Euler's doing. So here's x of t. I evaluate f, which gives me an arrow. And then I step a little bit along it by scaling by h, which is the time step. And then that's my new point, right? Okay, cool. Now, of course, notice that I did something wrong. I didn't actually solve the ODE, I only approximated it. You guys see that? Because like here, for instance, this vector field, which is like weirdly pixelated, kind of waves a little bit. But I didn't wave with my vector field, right? I just moved along a line segment, right? In fact, if we were really tracing out the path, I would like go down here a little bit. Yeah? And that's called error, really, in the formal sense. If you read a numerical analysis textbook, it's all about bounding error, right? You would like to bound the distance between the thing you got with Euler and the thing you would have gotten had you been able to solve this equation. Yeah? Notice you usually can't solve these equations exactly that way, right? F could be really complicated. Okay, so, right, so and a different way to put that is that the step size h, this amount of time that you move forward in each step, controls the accuracy of your system. And obviously smaller h corresponds to higher accuracy. Yeah? And so here's a picture of what that looks like. So here I think is exactly the same physical system you just saw in the vector field. You can see obviously if I take giant steps h, you drift farther and farther away from the current. Okay. Right, so as an example of Euler's method, let's say that I wanted to solve this ODE in the plane. Hopefully you guys remember ODE, it's ordinary differential equation. It's good math lingo. By the way, does anybody know the solution to this ODE? Can you eyeball it? I can. Yes?
This just result in a circle.
It should make a circle. Do you see that? Let's draw some pictures of these vectors. So let's say this is x and this is y. right? So when at x equals 1, this point's in the minus, so this is the point x equals 1, y equals 0, right? So then f would be a vector like that. Yeah. Similarly, if you work it up, it'll look like that. And so on. Let's draw some other. Right. And so the path that you get, of course, when you follow this thing, is a circle. Yeah. Raphael?
So then, would it be possible, like, if your dt is too large, that could make a spiral?
Ah, what an excellent point. So Raphael asked, like, what happens if your dt is too big? Yeah. Well, let's take a look at this picture. So let's say that I step a little bit along this curve, along a straight line. What just happened? Well, if my radius was 1 before, now it's a little bigger than 1 because I shot off the thing on the left, right? And similarly, every time I move along this thing, the length gets a little bigger. So Raphael's intuition is exactly right. What I get is not a circle. When I run forward Euler method, I get a spiral, and it looks like that. Yeah, great intuition. So the solution of this ODE, I'll let you double check this at home, looks like that. But in reality, if you do this numerically, and I encourage you to try this at home because it's 2 lines of code in MATLAB, you don't get this spiral, you get something that gets farther and farther, bigger, bigger, bigger. Yeah? And so now you can see why that h parameter matters quite a bit, right? You have to choose it in a way that is stable and accurate for the kind of window of time that you expect to need your system to work. Yeah? Yes?
Good question is that I was expecting the top function to be a function of t on the right-hand side.
No, it's a function of x. So in other words, this is telling you that the direction that you're moving is just a function of where you are on the plane. Yeah.
So it just has no dependence on t.
This particular ODE doesn't. Yeah. Okay. Right. So in other words, Euler's method is inaccurate. And in fact, something you can prove is no matter how small that h is, because of this fundamental issue that when you take a straight line, you're not on a circle, no matter how small h is, you will always trace out a spiral path. It's not like one of these, like if I make h small enough, it'll be stable. No? So the question is just like, can I, so then the next question you should ask is, well, okay, great, so I'll just take h to be like stupidly, stupidly small, yeah? Why would I not want to do that? Exactly. So again, remember this magic number, 29.97 frames per second. It's a good fist bump. Right. So if I have 0.000001 frames that happen in every th, I have to do a lot of those before I get to the next frame that I'm going to render. Right. And so that's computationally quite expensive. And so that's going to be one reason why we're going to want more accurate integrators that we'll talk about later on. By the way, this is not just like a theoretical issue. So for instance, here is an image from one of my own research papers. I thought I'd show you that I run into this problem too. So here I was proposing a method for deforming a 2D shape. So like you have this funny 3-headed, whatever this thing is, the dinosaur, and I pull its head and I want to see it, change, how it's posed a little bit. So this is like a tool that goes into Photoshop. And we show that if you do this in a stupid way, and I take the head of the dinosaur and move it up, down, and then back to where it started, look what happened to his head. It got like 3 times larger than where it started. Right? So here's the original image here. You can see he's roughly the same size as the other 2 heads. This is really a problem that shows up in this alpha, and one that we have to cope with in different ways. Okay. And so there are a lot of different ways to cope with this in practice. You can use different integrators, which we'll talk about next time. I'll also talk about implicit integrators, which will have a spiral that goes in instead of out, which is actually okay in a lot of cases because you at least prefer stability, right? Like if you spiral inward, then at least you kind of slowly slow down instead of going more and more crazy. And in fact, this is a really, really cool area that people in graphics care about quite a bit. So Euler's method is called an explicit integrator. Right? And so if I'm simulating a pendulum, like this little guy on a stick, then you'll get behavior that looks like what you see on the left-hand side, where slowly over time, he gets more and more velocity. Okay? On the right-hand side is what we call an implicit integrator. Let me play this one more time. You'll see he slowly grinds to a halt. That'll be like the backward Euler that we'll talk about next lecture. And for some physical problems, there's something halfway in between called a variational integrator, which doesn't preserve energy exactly, but preserves the integral of energy over time. It's an interesting property to have. Those are hard to do. Okay. So, right, so we now have a piece of machinery that says, okay, given an ODE, I can solve it numerically in at least a kind of reasonable fashion, even if I need tiny h to resolve the motion that I want. And now, of course, our other task today is to actually write down an interesting physical system to solve. Yeah? And that's what we're going to do for the rest of the lecture today. So in particular, in f equals ma, we've dealt with a. I think we all know what m is, so now our only job is to find f. And so a force, of course, is something that changes the motion of a system, and Newton tells you if you don't have forces, then your velocity does not change, and that's because you deal with a and not v. Yeah? Okay, so forces can depend on all kinds of stuff. It can depend on your location, time, velocity, your deep network, I don't really care. Whatever you need to make your video game have interesting behavior. And of course, your force is a vector, right? It's an acceleration that acts on you in a given direction, and the total force you experience is the sum of all these things. I think all this story is pretty familiar. So we'll start with the simple one. Of course, the force of gravity is a constant. It points down. If you're on Earth, if you're far, far away from planets, then you have to do that more complicated formula, which looks something like this, right? Where essentially planets act on each other gravitationally. I think we've all seen this in physics class before. One kind of funny thing, remember that smoke animation that we saw at the beginning of the lecture with this kind of funny, fiery-looking fluid? Essentially, all that was done to produce that was to take gravity and make it point up. Because if you look at smoke particles, what you'll see is that roughly they actually accelerate in the upward direction due to like what convection or some crazy physical thing that I don't totally understand. But I don't have to because I make graphics. That's the great thing. Okay. Of course, if you zoom out and you want to simulate planets, then you have what we call an n-body problem, right? Which is that every planet exerts gravity on every other planet. Now, something you might not have called out in physics class because it doesn't matter so much there. Is that there's actually a computational issue here, right? If I want to simulate a planetary system and I want the total force on a planet, what happens as the size of my planetary, like my constellation, grows? Well, I need more computational time to evaluate the total force on a planet, right? Because I have to iterate over all the planets and sum up these vectors to put to each of these guys. This is actually a huge issue, right? Because if I want to make like this super cool particle system that's like a bunch of bees flying in the air and all the bees are interacting with each other and zooming around in crazy ways, well, if I have pairwise interaction between every pair of bees, then simply computing the total force on a single bee is going to be very, very expensive. Yeah? And so this shows up all over the place, both in video games and in actual physical simulation. Right? So if you head over to like the planetary physics department at MIT, you'll see they also have algorithms that deal with these problems. For instance, there's a technique called fast multipole method, which can do this for planetary motion. Incidentally, they had a vote of top algorithms of the century. Apparently, fast multipole was one. I don't know who voted. Yeah. Okay. Right. So we have a demo here of what gravity looks like. So this is run on an NVIDIA GPU. So they're simulating n planets with n and not doing anything smart. And you can see here that they're able to do it in real time. But to get this to work, they had to do it on the graphics card. They couldn't just do it on like basic C++ code. It's really challenging. Cool. Okay. Yeah, and so one thing I mentioned on the side, of course, is that this is sort of a brute force algorithm. We'll be iterating over all of the planets and summing up the forces. But something we haven't proven is that that's the fastest technique, and it turns out they're faster ones. So one of them is called are these hierarchical methods, which essentially say, like, if planets are really far away from me, I can cluster them and replace them with like a big planet, kind of. And so this gives me some kind of n log n way of evaluating forces. And there's a very, very basic technique called that, which you will not implement in this class. One of my grad students is trying right now. It's difficult. Right. So of course, in reality, when we drop things out of an airplane, they eventually reach what we call terminal velocity, right? In other words, you don't just keep getting faster and faster and faster. Eventually, the resistance to the wind actually slows you down, right? And so the way to model that is to say that, well, if I am moving this way, in other words, my velocity points this way, I would like a force that points that way. Yeah? And so this is called viscous dampening, and the idea here is that I take minus some constant times your velocity, in other words, and make that a force. So this is just pushing against your motion. And this is a reasonable way to deal with wind resistance. By the way, it's also useful, remember, if stuff kind of spirals out, one thing you might do is say, okay, well, if I know Euler's method is spiraling out, maybe add a little force that's spiraling in. Right? And so a very typical thing, which is not physics, I can't say that strongly enough, would be to try and add forces to your system that just make it stable, because you know that otherwise it will explode. Now, this is not a physical thing to do. It's just because, like, in the scheme of things, if your video game like has pendulum, like, you know, you're making a kid's game and you're pushing your friend on the swing and slowly they start like spinning around. It's like pretty catastrophic, right? Whereas if your video game is slightly non-physical and dampens stuff out, it's not a big deal. Yeah? Okay. One other force that's pretty common in the graphics world, a little less so in physics, is to have what we call a spatial force field. So this would be the idea of, like, for instance, I have some planet and the planet doesn't care where I am because, like, I'm not quite that chubby, but I care a lot where the planet is because it's sucking me into the ground, yeah? So there's kind of this asymmetric relationship. In other words, this like kind of field of forces that exists around the planet rather than like a mutual dynamical thing. You know? This is an approximation. Right? Newton tells me that if the planet exerts a force on me, I exert a tiny, tiny force on the planet. But we're just going to ignore it, right? And so this would be a force that essentially just depends on your position. Yeah? And so there are a lot of times when you do this. In fact, a good way to do really low budget wind simulation is just to kind of manufacture an interesting looking swirly force field and just move particles around in that rather than to actually try to model, you know, things like Bernoulli's laws or whatever it is. And you can get some really interesting stuff. So for instance here, in this curl noise paper, essentially they say like, well, if I know roughly the direction of the wind and I know where there's some obstacle, I can just design a force field in the background that gives me pretty wind-like behavior. This is all purely engineered. I encourage you to read these papers because they're actually quite easy to read. They're just engineering. Like there's no physics there. So here's I think what this looks like. We got a lot of animations in the animation. Yeah. So all they're doing here is just kind of inventing kind of swirly looking arrows at these points. And you can see that when they move the particles around them, obviously you get very nice behavior. Again, no physics, just engineering.
What's the challenge?
What's the challenge here is to get what they call plausible velocity fields that still look like wind motions. Yeah. Which is not so easy. Yeah. Yeah, it's surprising you can do this. They're very, very simple methods computational. This is one of these sort of and then one additional force that matters in some systems is called, I think we call this the Leonard-Jones or 612 potential. Apparently here it's the MN potential instead of 612, which roughly says that stuff like really, really doesn't want to get close to each other, but they're also like slightly attracted to each other. Yeah? I think you've experienced this in everyday life. Right? Like, so there are a lot of particles where like you smash the particles together too much, they'll repel really quickly. But you know, maybe there's a little bit of gravity, so like it pulls them in just a little tiny. Right? And so this can be useful for certain kind of solid objects, right? Where like I really don't want the solid object to compress, but it comes apart a little bit, it's not a big deal. So for instance here, you can see we've simulated these balls with Leonard-Jones. So essentially once they get too close to each other, they just maintain a little margin rather than just collapsing into the ground. And notice, by the way, that by doing the interaction between that and the walls of this grid, what happens? Well, they actually maintain some kind of height. Yeah? So this looks kind of like a fluid. This is we're doing alchemy today. Yes.
Will this converge to a stable?
No, I think even the ODE will just continue bouncing around. I don't think this is distributed. Yeah, good question. Or here's another one. So people use this in fracture mechanics on occasion. If you don't have Leonard-Jones and you drop a bunch of particles to each other, of course the whole thing just comes apart. If you do this, then they repel in an interesting way, and you get this sort of explosive. Here's a third one, where here I think these particles kind of want to be together. These ones don't really care, and there's a little interface here that they're not glued on. And you can see very roughly you get some kind of tearing behavior. So the main takeaway here is that you can get pretty darn far by just engineering these pairwise relationships. That's a really surprising thing. Okay. One of the big challenges when you do this stuff is collision, right? I haven't told you what happens when these balls run into each other. Of course, in a sense, the Leonard-Jones potential kind of takes care of that, right? Because you can't collide. That force goes to infinity. Why is that kind of a BS thing to say in practice? Why does that not actually work? Well, if I'm simulating using forward Euler, then I might take too big of a time step, and I'll never resolve the fact that two things are running into each other. They'll just, multiply by dH and do that. Right? And then the Leonard-Jones force is still small. And it has nothing to do with physics and everything to do with just I took too big a time step. That makes sense? Okay. All right, so so for some more eye candy from NVIDIA, here they do a kind of a fluid flow solver and then inject smoke particles inside of the velocity field that they get after they simulate the fluid, and it looks pretty plausible. And this is run on the graphics card in real time, so like you could plausibly incorporate this into your video game. Although I think the reality of these video demos is like, if your video game had this, it could literally have nothing else. Right? This is taking up all of your frames per second. Yeah. But it's pretty convincing. Yeah, the kind of stuff that you can get. Again, this is not real physics, but it's remarkably close for what it is. Yeah. Yeah, it's remarkably fun to play with.
Is this supposed to be smoke or?
Unclear what it is. Yeah, I think what they've done is they've tried to simulate the kind of airfoil around the car, and then just to kind of visualize that they're placing little particles, and because they're graphics engineers, they've given them color. Yeah. But the remarkable thing here is these are like thousands of little particles that are vecting around. It's interacting with how the car is moving, and it's being measured. Okay. And if you'd like to see this demo live, you can go to Game Developer Conference 2009. Okay. There are more advanced forces out there. You can try to simulate, birds flocking in fish shoals. This is like its own little niche community of people that like are video game engineers, and they say like, oh, like our video game really wants to have this cool effect, and these characters interact this particular way. And here's this particle system kind of set of forces that we engineered that kind of looks like it, right? And then they'll have this kind of justification for like, well, I have this term because I want people to be attracted, but not too much. So then I have this other thing. Right? You can imagine it can get pretty arbitrarily crazy. One of the famous ones is for simulating flocks of birds. It's called Boids. This is for some reason another kind of popular project today, grade 7. Because it is true that this one's very easy to implement. Essentially, I think they say, well, birds are only really aware of the birds that are in this like kind of window around their face. So they add forces that try to attract or repel the birds that sit in that one. And because they can't see behind the tuchus here, there's no forces if the bird's behind you. And this is how they come up with their system. Anybody know what Boyd stands for, by the way?
Sylvester saying
Oh, like the cat.
yeah.
That's a concept. Apparently it's birdoid. Yeah. Although it also applies to fish, but only shoaling fish. I don't know what that means. But if you read his paper, he's very specific. It's only shoaling fish. Right, and essentially it's combined of 3 things, right? That birds don't want to run into each other. They kind of tend to align, right? So you look at the velocities of the birds near you, and you add a force that wants to bring your velocity to theirs. You do kind of want your birds to be in some kind of formation. Like you want to be the average of your neighboring birds. It's called lapashing. Yes?
What sort of data structures would you use to keep track of which birds are future?
Oh, well, that's a good question. So the simplest data structure is to not have one, and then just iterate over all the possible birds. There are a lot of different options from computational geometry world for maintaining these sorts of things. So typically, you use some sort of hierarchical data structure that, like for example, a tree that divides space up and knows that, like, really the only interactions are local, right? You just need to find the birds that you I think if you go to Piotr Indyk's class, you'll learn a lot about this stuff. Yeah, I used to teach that stuff at Stanford. It's fun. Or in this case, where really you only care about sort of the closest birds, then you really care about either Delaunay triangulation, like you just care about the little triangles of birds nearby. There's a technique called kinetic Delaunay triangulation, which is the world's biggest nightmare to implement in practice. Yeah. But anyway, so yeah, so this is what this looks like. This is made by Dimitri Trizopoulos. It's a very old video, but you can kind of see the Boids. There you are. And all these are, again, this is just forward Euler coupled with fancy forces. That's all that's going on. And you can see that the birds kind of flock. This is surprising. Right? So this is all to say that these particle systems are remarkably sophisticated for what they are. And that, like, very simple, it's again this theme that shows up in science, right? That very simple rules for interaction make very complex behavior of the whole kind of team moving around. Okay, you can similarly use Boids and have some kind of predator-prey scenario where maybe the birds tend to point more toward the prey, and the prey wants to run away, but they have different mass or something like that. But you can imagine different ways of engineering this. Right, so you have this invisible attractor, so the prey is trying to get somewhere.
I see trees of green, red roses too. I see them bloom for me and you, and I think to myself.
I don't think what's his face needs to contribute to the discussion. Right, so you can see that like these are just dynamical rules with relationships between particles. Yes.
So this is a particle system. Like wondering like where you could draw the line of like if you have like an AI like for Pac-Man, would you count the ghosts as particles and the like Pac-Man as a particle?
Yeah, I don't know. I mean, there's a philosophical question there, right? That function f could be really complicated. All kinds of if things, right? Like if Pac-Man is here and I see the cherry over there, then make the force like that. So in that case, you could probably what I would say is that the vocabulary word doesn't matter. Maybe the right way to put it is like you could think of this as a particle system. Although my bet is that the people that made Pac-Man did not have it. Yeah. Okay. And again, you can play with this. I've included a link in the slides to this little processing demo. Let's see. Here. Yeah. Yeah. So here, this is Boyd's running your browser. I believe there's some little interactive. See, like you can insert your own Boyd. Yeah. And you can see that he like zoomed off and interacted with the other guys, right? He kind of lines up with them and pushes his neighbors. Which is what this force is. Yeah? This is a really fun demo, by the way. I like totally killed hours in my office. This is what happens when you don't come to office hours, by the way. Right. Okay. Okay. And of course, I'll let you take a look at home. The website for people who uses something a massive scale. So for instance, you know, if I have Lord of the Rings and I don't even know all the names of all the little guys that come charging in at each other, and you know, there's the Jets and the Sharks, and they're getting in a fight, and you know, they come in, and to some extent, when these people are charging at each other, they're not really intelligent beings anymore. They're just like particles that want to jab their spear into the other guy, right? And it's pretty easy to write some rules directing that kind of motion. And roughly, that's what they use in these movies, right? Because you couldn't possibly hire an animator to simulate, you know, your millions of trolls that are all blasting at each other at the same time. Right. So let's see. This is an example of a particle simulation, early Lord of the Rings here. And so probably in reality, what happened is they had mocap for like the first couple guys on the scene that the camera focuses in on, and they have a particle system for the rest that's just simulating their motion and making sure they don't run into each other. Yeah. Right. Because like we don't have the kind of money in the animation studio to hire an animator to animate every single one of these people. That would be expensive. Yeah. So anyway, this is yeah. So this is used in practice. It really is the reasonable trick. Okay. So again, remember that particles come from emitters. There are a lot of different ways to design an emitter. It would be a pretty boring emitter if it just generated one particle per second, right? We're just getting the little guy cleaning stuff up. So typically, what you do is maybe you increase the probability of emitting something as a function of time. So like if I haven't spat out a particle in a long time, then part of the probability of spitting one out increases, and that's roughly how that's being communicated. Yeah? And so there's all kinds of cool particle controls out there, where essentially people that design video game software don't want you to code this yourself, but instead maybe you download the Max Payne particle editor, Particle FX, which essentially allows you to very intuitively write down the kind of relationships you want between your particles and engineer the cool motion for your video code. Right? And so they have these cool tools where essentially rather than writing down specific force functions, like if my bird is this way, then do that, I can just draw them as a spline. Right? So for instance, maybe I know the distance to the closest bird in every radial direction, and then I write down my force as some function. Yeah? These are things that no artists can do. We're slowly putting ourselves out of business in the technical side. And similarly for emitter controls, maybe I have some emitter that, like, if I haven't emitted a particle in the last second, I want to spew one out, you know, even more and more and more because I'm like building stuff up. But then eventually my volcano runs on a lava, and I want to slowly turn my particle off. Right? So these are all the sorts of controls that you find in video game development. So here, let's see if we can see the Unreal development kit. It's one example of this. This is a really boring video. Yeah, so So anyway, you can, I'll let you watch this at home. Essentially, you can see that as the artist changes the different relationships between the particles, they get to like literally preview the particle system on the left-hand side and engineer it to the left. Yeah, it's fun. It's like playing God, right? I mean, you're essentially coming up with the laws of the universe, so you get the physics you want. Right? It's pretty different from course 8. Okay, right, next. Okay. Of course, particles are little dots, and if you render them that way, they're pretty boring. So one trick to make your particles even more interesting might be to render a little tail behind them, right? So oftentimes when you render sparks, for example, maybe what you do is draw a line between the last few particles so you see a path rather than just a single line. Yeah? So this is pretty typical in sparks and bullets and things, in which of course people put lots of effort in the graphics world just to be as accurate as possible. Oftentimes the particles don't really contribute to the Z buffer. In other words, like I don't have a particle that goes on top of another because they're like a little transparent anyway. This is kind of a computational trick that we'll talk about more when we talk about Z buffers. We'll worry about it. And so you can see here some examples where essentially probably what happened is that in Metal Gear Solid here, they're really only simulating like the very tip point of these sparks, and then what they do is they just keep the last few time steps around and render a line through them. And that way it kind of looks like a fire shooting out. Yeah. These are the tricks of the trade. So for instance here, they've not only, instead of rendering a line, in fact, they've rendered what we call a billboard, so like a little rectangle with explosion-like texture, like some little blobby thing. Right, so roughly, you know, I have a particle, and rather than just drawing it as a dot, every time I draw the particle, I draw some little cloudy thing. Right? And maybe this thing is slightly transparent, so when I put them all together, I get a pretty complex looking cloud, even though really this is just driven by like its center point. Yeah? See, so these are the sorts of tricks that we do in realistic effects, and this is called a billboard or a sprite. Right? And the reasons that typically, well, for one thing, this is stored as an image. It really is like a little billboard with a transparency value, so you don't see the edges. These usually have the property that if you move your camera, like you rotate your camera a little bit, the board just stays facing the camera. Right? Because otherwise, well, you guys could tell me now that we know about perspective what would happen, right? Like you go to the side of your explosion and suddenly your like explosion would like kind of shrink, which seems like a bad property. Okay, and you get some pretty cool looking stuff, right? So for instance here, so on the upper left hand side you can see these sprites that they've combined to make an explosion looking effect, and the result's pretty convincing. Right? So I think the real takeaway here is that you can get really complex looking things with very simple rules. Yeah, and so this dates all the way back to like 1982, 1983, where if you watch Star Trek II, The Wrath of Khan, and I encourage you to because it's like painfully dated, you'll see a lot of these old school effects. Right, all right, here's another little particle system. Okay, so that's actually it for today. Are there any questions about particle systems, how they work? Yeah.
What was the fractal landscapes link on the other slide?
Fractal landscapes. This is a procedural way to generate stuff that looks like the ground. Right? So fractals, remember like these crazy rules for taking line segments and dividing them into more line segments that are kind of pointy. And in Star Trek II, historically, not only did they use particle systems to like show stuff exploding out of some planet, or it's been a long time since I've seen this movie, but they also, you know, like the surface of the moon is generated procedurally. Like they're really evaluating fractal. Okay, folks. So with that. I guess I'll see you guys on Tuesday. Remember that you should start your homework. Please start your homework. It'll be due on this coming Wednesday, and the homework after that you'll get to implement a lot of the stuff we just talked about. So Euler and classical.